All right, welcome everyone. Thank you for joining us today. We have an excellent webinar planned up for you. Raj, do you want to kick us off? Yeah.
Indeed. Good morning, good afternoon, good evening, good night, wherever you are from. Good day. Welcome to the Womanium and E.ON talk, Unlocking the Future, looking at the research and quantum computing innovations at utility leader E.ON. A little bit of introduction about Womanium and also E.ON. Let us start with E.ON. E.ON is the largest energy utility provider in Europe, and therefore, whatever E.ON does has got global impact. And E.ON especially is at a critical point in its history, and we will come to that. Womanium is based out of Washington, D.C. We create the next generation of female scientific leaders. And in that capacity, we work with all the leading US government agencies and labs. Our first partner was the US Department of Energy's elite research funding agency called ARPA-E. And ARPA-E funds cutting-edge innovations in the energy sector, everything from battery to grid to nuclear to solar to grid systems to transportation. And we work with ARPA-E on 35 of their creative energy innovation programs as our first partner. Since then, we have worked with all the leading US government agencies from DARPA to NASA to now the National Institutes of Standards and Technology and many of our Department of Energy partners in the realm of quantum computing and sensing. And this talk is the beginning of a solid and deep relationship across the Atlantic between United States and Germany, between Womanium and E.ON, looking at the future of energy, quantum systems, quantum computation, and innovation in this sector. Germany is a great industrial power, and E.ON powers that industrial powerhouse. Therefore, E.ON is very significant, and whatever that they do is going to be extremely important for Europe, for Germany, and the future of energy. And coming to Germany, Germany has a long and deep role in the field of energy and also quantum physics. In fact, many of the great quantum physicists have been Germans, and many of the great innovators in the field of energy also have been Germans. But in the last 50 years, some of the greatest industrial innovations happened from the United States, from light bulbs to many of the developments in automotive sector, computing, space, GPS, satellites, and more. And Womanium works with all these partners. So at a critical point in the history of the world, when the world is transitioning from different forms of energy to new forms of energy, renewable energy and other forms, and when E.ON is leading that, and also at a point when the automotive sector is transitioning to electric cars, and E.ON has to ready themselves to meet that demand for energy systems, expand their grid, optimize their grid for electric vehicles. This period in energy transition requires new kinds of innovations, that requires new types of computational systems, simulations, and that brings us to looking at the work that is being done at E.ON, specifically in the realm of energy. And this is a slide about Womanium. Womanium was founded in Washington, D.C., and Prachi will take over from here. Over to you, Prachi.
Yes, thank you all. In fact, very quickly on where quantum and energy intersect, we have Vardaan to share it with us a little bit more. Please go ahead.
Yeah, so we have worked with a lot of exciting partners over the past couple of years. We started Quantum 3 years back, but since then we have worked with some of the best quantum companies out there, but not just quantum companies. We have worked with many interesting agencies like Deloitte, Ernst & Young, and many educational institutes like MIT, Stanford, Princeton, and all. But the best part of our collaborations have been the interesting national labs and the exciting work they are doing in the research domain, from NASA to NREL, Naval Nuclear Lab, and many, many others. And while working with all of these amazing partners, one thing which we have realized is that quantum has the potential to impact a lot of different industries. And it doesn't really matter at this point which industry you are a part of, or maybe what work you do, or where you are. Sometime in the future, you will definitely get impacted by quantum technologies in one way or the other. In today's webinar, we'll be focusing more on the quantum computing use cases for energy and grid network. And just to elaborate a little bit more on that, quantum technologies impacts the energy grids in a variety of ways. Quantum computing is definitely one of the main strong points we'll be discussing today, but others too, right? From using quantum secure communication to protecting against attacks to grid controls. And this is very, very important. It's in fact one of the priority use cases in many national governments too. Like, how do we safeguard our communication systems against potential quantum hacks and attacks. So we do that by using quantum secure communication. It could be in the form of QKD, or it could be in the form of post-quantum cryptography, or something in a kind of a mixture of both of these technologies. But the main point is, how do we safeguard our communications today? We are also using quantum sensing, which is, I would say, one of the highest TRL level technologies over here compared to quantum communication or computing. We are using quantum sensing for detecting different kinds of physical anomalies, be it possible electric or magnetic, or let's say temperature variations within the grids. And how can we detect them easily and with more efficiency while working on these grids to make them both smarter and more efficient and resilient to potential attacks. Today, like I mentioned, we'll be talking more about quantum computing. So let's just dive into that. Quantum computing could be potentially used for fault prediction, where we're using quantum neural networks to quantum annealing and many, many other technologies. But not just that, we are also working on optimization to minimize the cost, but at the same time, fulfilling all the energy demands from the customer's end, which is a very complex combinatorial problem to optimize. Quantum computing has a very good potential, and we are already working on it with E.ON. And we have some other use cases too, but I won't spoil the fun by elaborating everything here. I will quickly introduce the webinar. Today's webinar is part of the Quantum Solutions Launchpad. QSL, or Quantum Solutions Launchpad, is a program by Womanium where we partner with some very amazing organizations, including NNL, the Naval Nuclear Laboratory. For those of you do not know about NNL, they were in fact the first organization to develop the world's first nuclear submarine. Amazing, right? We also work with Fraunhofer Institute. Fraunhofer, in fact, invented the first time MP3 format, the format which we all use day in, day out for storing our audio files, MP3, that was developed by Fraunhofer. And we are very privileged and proud to work with all these amazing organizations on the quantum domain and develop some very exciting use cases. These range from working on quantum software, which led to some runtime speedups up to 90% and like actual value reduction over there. We also worked on creating some very important applications for the industry itself for warehouse optimization. Then we had teams working on quantum sensors. It was a more hardware-oriented project. The entire goal was to create portable and low-cost quantum sensors, which could be designed and implemented in the field. Very exciting stuff. It's due to be patented right now, but yeah, a very interesting study which the team undertook. And to take this forward and to keep the momentum going, we are very proud to announce today our next partner, E.ON. So this is a time where I would like to introduce all of our speakers and the panelists we have today. We have, we have in today's webinar, Dr. Munib, who is the Sustainability and Innovation Managing Director at E.ON Group. We have Dr. Jan, who is a Deputy Head of Research and Technology at E.ON. Dr. Corey will also join us, who is the Chief Quantum Scientist at E.ON. And finally, Celine from E.ON will share more about what it is to work in and at E.ON. So very exciting webinar plan for all of you today. A quick point to note for all the participants, the agenda written on the right side of the slide right now is what we'll be following. So just, take care of that. Please keep the questions coming on the Zoom chat. Try not to unmute yourself, but videos are welcome always. And we'll take and moderate all the question answers at the dedicated slot during the webinar. So this is a good time for me to stop sharing my screen. Jan, it is the stage is yours, and please go ahead and share your screen.
All right, thanks for the kind introduction. I think Munib, you would like to take over the first part.
Yes, if you could go directly to the next slide. Just to give you an overview on what E.ON actually does. So E.ON is a large utility company that is active across Europe, from the UK to Turkey, from Sweden to Italy. But a lot of our business is still based in Germany, where we originally come from. So our business focuses basically on three pillars that you can see here. Energy networks, so we are the largest distribution grid operator in Europe with 1.6 million kilometers of electricity grid. Then the second pillar is E.ON's energy infrastructure solutions business, where we basically support our industrial and commercial customers, but also municipalities with infrastructure solutions like district heating, for example, or electric charging infrastructure. And the third pillar is energy retail, where we provide our 47 million customers with heat and electricity. Now, our role has changed over the years. We used to work basically in the background, make everything work with anyone knowing it. But now, with the energy transformation going on, we have taken a much more active role, and we shape basically the energy and the energy system of the future. And yeah, with that, I already hand over to Jan Schiefelbein-Lach, who will talk about our challenges in that field.
All right, thanks, Munib. Yes, I would like to dive deeper with you into our research challenges and potential solutions we are working on. And maybe to make it a little interactive, so you already heard that we are one of Europe's biggest or largest distribution grid operators. So this is one of our main grid challenge. So coming from a few hundred to over 1 million. So please write into the chat, what do you think am I talking about here? Coverage towers, distribution, I see. Distributed networks. Computational needs, yeah, talking about data. I see a lot of good ideas. Grid size, yes. Scaling. All right. You're on the right track, definitely. A lot of things. It's absolutely correct what you're writing. So let's say one of our main issues is this European change or worldwide change from centralized large-scale power plants to millions of small connected devices like PV or wind power systems. Actually, the 1 million was just reached only for Germany for all the devices connected to only the E.ON grid, just to give you like a feeling for the size of this challenge to us. And to dive a little deeper, so we have this shift from centralized power plants to this millions of decentralized generation units and appliances, and we have to manage that. And so there's necessity for smart solutions and innovation. You can see let's say the old world on the left-hand side with these large power plants, which were, let's say, kind of flexible enough to just provide all the consumers who are inflexible with electricity what they needed. And we had separated worlds for combustion engine cars. And at least for Germany, we had, well, mainly gas or oil powered heating systems. And we are now changing to, let's say, the new world where we have a lot of decentralized energy systems or renewable systems on different kind of voltage levels, so on the higher voltage levels as well as on low voltage levels at the end consumers. You can just put a PV on your house and rooftop. And of course, we got further electrification with, for instance, heat pumps or air conditioning units, electric vehicles and chargers. And we see also new solutions for instance, industry. We have smart processes or other energy carriers like hydrogen. And we also see new kind of heating solutions for city districts, like low temperature networks, like our Ectogrid. And all of this change, like in all domains, results in a couple of challenges specifically from the grid perspective. And first of all, Munib already pointed out, we have those 1.6 million kilometers of grids and roughly 50 million customers where we need to ensure reliable grid operation. So all of you want to have like electricity at your house 24/7, and our life is driven by electricity, and we need to make sure that our grids do their job. But what we also see, you wrote it in the chat, that we see more and more decentralized energy resources being integrated into the grid, like wind or PV. So we got less stabilizing, rotating mass or damping mass of the power plants, but more fluctuation, more dynamics. And it's also harder to predict, especially on distribution grid level. You need like really accurate, for instance, weather forecasts. We'll get back to that point, by the way, later on, so keep that in mind. We also see challenges in observability and control, because at least for a lot of German grids, it might vary worldwide where you live. A lot of German grids, specifically on low voltage level, we are kind of blind So we don't really know what's going on, what systems are working from the old perspective as it changes. You need to think about where to place measurement devices and what are the remaining parts you need to simulate or kind of calculate to know what is going on in your grid and how, let's say, sure you are with what you are doing. Another thing, the grid enhancement, of course, building up new grids, enforcing the grids which are existing. So it's on the one hand side about smarter asset management, ideally to use smart approaches to know when or to what extent some devices might fail and when you have to replace them. And of course, with all the grid enforcement and the, let's say, the enhancements we have to do, we have a limited workforce, but there's a lot of things to be done. So where to put our resources on? So like an optimization problem under uncertainty. Flexibility, so flexibility utilization. So how to enable flexibility in a smart way, especially from grid versus market perspective. Because if you all switch your EVs or chargers on or heat pumps at the same time, it might be interesting from cost perspective as end consumer, but it might cause some challenges for the grid, right? That's an issue. And of course, with all the, let's say, sector coupling and now more holistic planning, this change from the old world where you had like separate planning in a lot of cases to interconnection, you need smarter ways of planning what you are doing and how to bring mobility, heating, and electricity together. Another important aspect for us, also probably for you, it depends on where you're working on, cybersecurity. If we got more and more devices interconnected, we see other attack vectors, and we need to take care of that. Also with new ways of, for instance, AI usage. And looking at our people, I mean, you have Celine with us today. She will probably going to talk a little more about that. But with the tremendous growth in the grids, so how can we train our workforce and also make sure that everyone comes home safely when working in the grid? It might be risky. And also, how can we, let's say, smartly assist people with, for instance, AI chatbots, etc., what is probably all known to you well. And last but not least, but an important part is the protection of vulnerable groups. So thinking about the social economic fairness of what we are doing. Because with the energy transition, you might see rising energy prices, which have a higher impact on vulnerable groups. And how can we actually let them participate on this transition and on the new mobility and heating transition world? So you can already see there's a lot of challenges related to the physical assets, but it's, let's say, kind of impossible to do everything manually. So you need digitalization and innovation to tackle these things. And because there's so much going on, it makes us also so interesting to work in this sector right now. And with all these challenges you just saw, we as R&T derived our main research programs and tasks you can see over here. So maybe a quick introduction on research and technology. So what we are doing. So we are mainly partnering up with leading scientific institutions like RWTH Aachen, like a TU Munich, ETH Zurich. We're also working with Cambridge and Stanford in the US, which might also be known to some of you in the Bits and Watts program. And our main task is to strengthen E.ON's playmaker position with, on one hand side, strategic projects, on the other hand side, business-related projects. And what you can now see on the right-hand side are different programs. So first of all, the Sustainable Decentralized Energy Systems program, which mainly tackles the question how the future energy system looks like to be resilient, to be sustainable, and also social economically fair, basically tackling the challenges you just saw on the prior slide. The Future Heating and Cooling program, basically tackling how to decarbonize heating and cooling with heat pump usage, smart home technology, like low temperature heating grids, geothermal usage, etc. And going a little deeper, there's a deep decarbonization program, mainly looking at what are reasonable and also for us practical pathways to get to net zero. Also looking at future energy or let's say renewable energy carriers like hydrogen or ammonia, and also at negative emissions, for instance, how to get emissions from the atmosphere and to store it away. We're also looking at technology foresight, so basically looking at game-changing technologies, which might be of interest for us as utilities. And also, of course, we are into knowledge dissemination within the company, but as well as to the outside world. So Munib, for instance, is a lecturer at Stanford that made lectures over there. And we are also eager with talent development with scholarships, exchange rounds, and also a reason, of course, why we are cooperating with Womanium, which is a very great way, of course, of bringing new talents into the STEM world. All right. So how do we create value? So it's primarily two types of projects. So first of all, strategic projects, and on the second, on the left, or the downside, not downside, it's the wrong word. The second one is supporting business initiatives. And it's all about, okay, getting close to business, supporting what they really need. So diving into some examples of strategic projects, that is, for instance, direct current applications to see how we can use DC in distribution grids to enhance capacity or increase resilience. We already talked about negative emissions, so how to take carbon dioxide away from the atmosphere and store it away, and of course, hydrogen supply chains. As a disclaimer, these projects already, let's say, were done like 2 to 3 years ago, but now having an impact of what we are doing as businesses E.ON today. And of course, we got some business initiatives which are really close to products E.ON is doing. For instance, we got the IQ Energy World, so some products done by our colleagues of E.ON Energy Projects. So looking at smart ways or smart algorithms to, for instance, schedule combined heating and power systems in industry, taking into account energy markets as well as the production processes. We got the Ectogrid. It's a low temperature heating network where it's mainly about, let's say, shifting heating energy to different temperature levels with heat pumps, so you can do cooling and heating in both ways, specifically interesting for densely populated areas. And last but not least, how to bring in AI into grids with GridCube. And that's where I would like to do a little deep dive together with you. So what we are doing with AI in grids. So you already heard that we have a high increase in decentralized appliances with EVs, with heat pumps, specifically in the low voltage grid. And all the dynamics and volatility cannot be covered by just putting more copper into the ground. Of course, we could say if you get paid for that, that's great, but it's not what we want. It's not really working and not really efficient. So we need to think about other ways of doing this. And there's also a lack of observability in many low voltage grids, as talked before. So we need solutions to account for that uncertainty. And the idea was, why not take in an AI-based device into the grid, which can steer the grid or control the grid from grid perspective, also under this incomplete information. But of course, it needs to be really reliable because the system has to work all of the time. And it needs to be efficient in decision-making, meaning need to evaluate fast in what it's doing. So the general idea was having a pre-trained physical device. I mean, you all know that basically. So having this physical box could also be your smartphone looking at something handwritten and immediately telling you that's a 7. So, I mean, this is all well known to you. So what's the trick behind that? And the thing is, okay, how can we transfer it into the grid world? So when you now look into the grid, left-hand side again, it's basically a graph with nodes and edges with different time series related to it. And now again, we have a physical pre-trained device with some grid knowledge, with some measurements for evaluation, and leading to, let's say, fast and robust decisions on what it's doing in the grid if we have to do something. Of course, we don't want to, but in case you run into like an overload, you maybe have to curtail or at least react. But why are these concepts not that frequently used in grid planning or operation? And the thing is, when you think about the prior slide, like text recognition or classification of pictures, you have cats and dogs, and something went wrong there. Normally, no one is really harmed, right? So if it's maybe just for the cats and dogs figure, if you see a cat and the system tells you it's a dog, it's basically hopefully just funny. But if you have a wrong classification in the grid telling you we have no overload, but there's an overload, it might cause real trouble. So we need to be well aware of what we do when we bring AI into the field, which makes it a harder challenge to tackle. But we thought, let's do it together. It was an idea by one of our DSOs, the Schleswig-Holstein Netz GmbH. And we initialized together with them and with RWTH Aachen University a collective project. So what is the concept? What's the idea behind that? So we developed different AI algorithms which were pre-trained in the cloud for the grids and then put into this little device at a substation. So it's a transformer station, basically, where you could do some basic measurements, but in ideal case, you have further measurement from the underlying low voltage grid over here. And also, with not having like all customers or grid points covered with measurements, the system should be able to detect like critical states and then react at that parts of the grid where it's able to control different kinds of loads. For instance, at an EV charging point, curtailing and shifting some of the loads to a later time to keep the grid in a stable condition. All right. So we developed different kind or tested different kind of approaches like graph neural networks, reinforcement learnings. I guess a lot of you will know about that methods. And we entered a lab test with real low voltage grid and real appliance to see how it works under real conditions. And it was pretty interesting to see that, for instance, the reinforcement learning agent was really effective in detecting and mitigating all the critical states we put onto the grid, also with really low measurement information. So the lab test for us was a big success. And also we saw with the pre-training in the cloud, when it's a nice thing of AI, right, that we could put it onto like simple hardware. So the colleagues tested it on a Raspberry Pi. Actually, now it's on a specific edge device you can see over here, which can also be brought into the field. And that's the thing what we are doing right now, that we are in the field with real voltage grids or low voltage grids with one of our DSOs to see how the system works within the field. All right, that was a quick overview of what we are doing at Research and Technology, and I would like to hand over to my colleague Corey for the quantum activities.
Yeah, perfect. Thanks, Jan. Can you hear me okay?
Yes, we can hear you.
Okay, excellent. Yeah, so in some minutes, I'm just going to give a quick overview of the quantum computing activities that we do at E.ON, as well as one particularly interesting use case that we've been working on for the last little while. So as a little background about the quantum computing program, we started it in 2019, just before the pandemic. We have access to two different kinds of quantum computers. We're a partner with IBM Quantum, which gives us access to their fleet of quantum computers in New York State and also several in Germany. And we also are a customer of D-Wave, so we have direct access to the D-Wave fleet of machines for the quantum annealing approach to solve optimization problems. And yeah, we consist of a team of full-time quantum engineers on the team. Plus, we supervise master's and PhD students through academic alliances through various different universities and collaborators. We're working with like Technical University of Munich, the University of Munich, RWTH Aachen, University of Oxford, and DTU. Next slide, please, Jan. So what types of problems are we looking at? So basically what we're doing is we're trying to find places where quantum utility may be reached in the energy sector. So the search for quantum utility sort of is happening in many different sectors across the world. And it's extremely non-trivial to do this and to actually prove this rigorously and legitimately. So what we're doing is we are looking at all kinds of different use cases across the whole company. So this means like quantum optimization problems. We're looking into things like V2G, so vehicle to grid. This is where you are able to charge and discharge your electric cars, like your Teslas are plugged in. How do you do smart charging, but also smart discharging to maybe market that extra energy in your car battery? We also look in things into peer-to-peer energy trading, which is what I'll talk about soon. So this is how do you optimally use your excess solar generated energy. If you have solar on your roof, yeah, sure, you power your house, but maybe you want to power, your neighbors' houses who live a few doors down from you. So instead of them getting power from, a remote energy generation station, and having that transport all the way through the grid, I mean, you should kind of use local energy. This involves a problem called community detection. We're also looking into things like dynamic tariff pricing. So how should everybody, in Germany or in America, get a customized energy tariff? So imagine instead of paying a monthly fee, or sometimes you have a time of use tariff where energy's some price during the day and then cheaper in the evening. Since energy is procured on an energy market, it actually changes price every 15 minutes, every 30 minutes, every hour of the day. And we as consumers don't really notice that, right? But what if you could price everyone's electricity based on their individual usage and the current market rates? And then even looking into things like, at certain times of the day when you have more renewable energy flowing into the grid, you might want to offer a discount. Yeah. We're also looking into quantum machine learning. So this is applications, most methods using something like quantum kernel methods, looking into predictive maintenance of power plants and high dimensional time series data or classification problems. And as well as applying techniques from quantum computing for finance, so things related to energy economics, so how to kind of price options and contract pricing, or doing portfolio optimization. You go to the next slide, please. Perfect. So the one use case I wanted to just give a very high level overview for is something that we've seen some promising results lately. So this is on the topic of peer-to-peer energy trading. The idea of peer-to-peer is a little bit what I touched on earlier. So hopefully in the future, everyone has solar panels on their roofs, and you are generating your own electricity from the natural energy source. I mean, the sun. It's a bit silly we don't use it any more than we actually do. And you're using it to power your house. You might have a little battery in your garage or something. And how do you send this excess electricity back into the grid? So it goes into the low voltage grid, which we're all plugged in our neighborhoods. And then you want to basically distribute that energy to people locally around you. And if you have smart meters, or you have digital meters, then this tracks sort of the amount of energy you kind of put into the grid. And what you can do is look at the power flow of this electricity, but how it kind of goes into the grid and kind of dissolves. And the idea would be, how do you optimally sort of figure out when and where to inject that energy to maybe trade it, creating like a local auctioning algorithm to sort of trade it with a neighbor for some kind of price. So the overall idea would be, you sign up for such a service, you're generating revenue as an energy seller, your excess energy, and you're not going to be on your phone like picking your energy price and things, some cents per kilowatt. So this needs to be done kind of automatically, and at the end of the day you get a cheap energy bill, or you maybe even make money at the end of the month. And so this is all for the purpose of using local renewable energy. So how do you exactly optimally do this? And what's interesting is this has really nice connections to game theory. So how do you figure out, if you have a whole city and you have the whole electrical power lines that connect all the houses in different suburbs, you could separate people into groups by area code, let's say, or you can do it a bit more intelligently and try to look at the grid structure about how the power lines are all connecting all the houses. And you, of course, don't want to overload the lines, right? So because that will cause a blackout. So, or it may cause a blackout. So what you want to do is figure out the best way to transfer energy across this fixed infrastructure, and group houses together in an optimal way, such that they may trade energy all together. And this changes throughout the day, right? So every 15 minutes, every half an hour, a cloud may go over your neighborhood, and then maybe you're not making solar anymore, right? So if you go to the next slide, Jan. Forgot to mention, this is work with Aquarius. It's a startup from Munich. the University of Munich, and also the University of Oxford. And what you see here is a very nice graph. And what you see is the thickness of the lines connecting the circles corresponds to the power flow traveling along an electrical line. The circles and the colors are houses. Blue means they're producing energy. There's excess energy. And red means they need energy. So it's in kilowatts. It's been scaled a little bit, but you can see this is some kind of fake artificial neighborhood that has some supply and demand, okay? And then the problem is, if you change to the next slide, please. Here we've identified grid partitioning, where you can see we have 1, 2, 3, 4, 5, 6 different partitions where these players in this game are able to optimally sort of share their energy. And so the people that are producing it can share it locally, and the one that need it can get it locally. And now this may seem like very simple and with a couple of circles with some colors, but it's actually an extremely difficult problem. Can you go to the next slide, please? So the best classical approach to solve this, is called a coalition structure game. To do the general problem, if you look at number of buildings versus time, and you try to run this on classical computing, it has an exponential scaling. So to do 16 buildings only takes about 10 seconds. To do 18 buildings, it takes 1 minute to solve this optimally. And to do 20 to 21 buildings takes 16 minutes. And if you put 2 seconds of thinking into this, you realize that, okay, this will never work for a whole country. This will never work for a whole city. This will never work for a suburb, right? So we need to relax the problem to even make it actually solvable. So can you go to the next slide, please? So what we did is we relaxed it to a simplified problem called the induced subgraph game, where we're computing really the power flow, the optimal power flow between everyone in the grid with slightly relaxed kind of constraints. And what we showed was on real quantum hardware, we're able to run it on quantum chips, and we can scale it up. It can fit about 400 buildings right now on today's quantum hardware. And here you see the limit of 10 seconds, and you can see the classical is the gray, and the green is the quantum solution. And if you notice, the 2 lines get closer together as you move to the right-hand side of the plot. And the green line is actually flatter, right? So if we extrapolate and we extend, so please click next. We can extrapolate the curves, and we expect that they will cross around 700, 750 buildings in these in these calculations. And at this time, what this would mean is the solution quality is the same so far, up to 400 buildings. However, the quantum one will hopefully be faster if we follow the trajectory of the current experiments. It's hard to say. We need to wait for the quantum hardware to be a little bit larger to be able to do this large experiment. Nonetheless, this is a good proof of at least a preliminary scaling advantage on real quantum hardware. And this is where we would see the expected so-called quantum utility, where it can outperform classical computing problems for a real business problem. So with the next slide, please. We want to talk about the Womanium Quantum Challenge. So please, next slide. So what we're doing is we're working with Womanium right now. We're looking for a team of gifted Womanium fellows to work on us with a different project. And this project involves something about time series forecasting. So in data science, time series forecasting is, a standard thing that every student learns. And there's a lot of interesting work going on right now using quantum computers for time series forecasting. So the jury is still out what kinds of potential quantum advantage there may be. So this is why we want to really look into this. So, the question is, how can we leverage near-term so not fault tolerant, near-term quantum computer algorithms to more accurately predict local energy demand. So in this plot, we see some energy demand in some city in Germany. So just a nice forecasting problem. And so we're really looking forward to working on this for the next months. And with that, I would hand over to the next speaker.
Wonderful. Yeah, thanks a lot, Corey. Thanks, Jan, for giving us a very high-level overview and then diving deep into the various quantum applications. We have a lot of discussion going on in the chat. You raised some very interesting points, and the participants took it forward. And just, yeah, they are very busy discussing a lot of different topics. But I think this is a good time for at least, answer some of the questions we are having. I'll quickly pick one or two questions for you. So one question, I think that question very well relates with the project topic on the screen as well. With the varying energy demands and at the same time putting renewable energy sources varies the amount of energy getting produced as well, how do the energy utilities manage the pricing for energy?
Okay, I mean, give it a shot. So basically, I mean, you can talk from the grid perspective first of all. So the grid, of course, is basically the situation you want to get the energy, so we need to deliver it to you. It's bringing it from A to B, right? So you could say in a sarcastic way, from the grid perspective, not really caring about the prices, right? So of course, it's a thing that renewable generation is really cheap, right? On the other hand, that the prices at the end consumer, especially in Germany, I think we wrote it in the chat, right? So you're pointing out, well, they are pretty high compared to other countries. The other countries having the same problem. So there's a gap in between. And we need other, let's say, smarter methods, of course, to account for that. Because beforehand, when you had your fixed pricing and that's the perfectly flexible way of steering larger power plants, it wasn't an issue, right? But now we have that. We need to think about how we can really store and also say use the cheap energy when it's there, right? And that's a challenge, right? And so it's where basically my colleagues are working on the field of consumer innovation to think about like flexibility markets or other ways of, let's say, having a smart algorithm at your home, which is doing the trading for you to make the best benefit out of it. And dealing until I have to step in, let's say when the flex market is not taking care of the grid, then we are heading back with what you saw, like with the grid cube, then we might have to curtail or let's say look that the system stays in stable boundaries.
Maybe just briefly to add on that. Now the way we price electricity in the future will have to change fundamentally, because we're coming from a system that was resource-based, where we priced electricity based on the price of the fuels. Now, if we go into renewable energy, there's no fuel. So, and the additional energy that we produce is basically for free. But the investment behind that, in the infrastructure behind it, in the grids, in the electricity production facilities, and so on, is huge. So the cost is not zero. It's the requirement for investments is large, and that is why the electricity market needs to be transformed step by step. But it works differently in every country, and it would be worth another talk to answer that question.
Right. Thanks a lot, Munib. Thanks, Jan, for answering that question. I have another question coming in from Sophia. And the question is that, are you also checking on the sustainability of artificial intelligence in quantum systems? Because in the future, we don't want a scenario where on one hand, we are trying and using quantum for reducing the energy prices, but at the other hand, those quantum resources are themselves taking up a lot of energy.
Yeah, I'll take this question. So I think it's a bit of a misnomer about the amount of energy that quantum computers use. So they do use, of course, a lot of energy, but I mean, it depends on the type of quantum computer, first of all. So if you're talking about superconducting qubits, that's one. There's also machines that are made with NV centers and diamond wafers that can operate at room temperature, right? They're still qubits, though. even if you're talking about supercooling and you cool the chip down to a few millikelvin, you get it cooled down just like any university lab. So every university in the world has multiple, dilution refrigerators. When you get it cooled down, it takes some energy. It's not an exponential amount or anything. And in my opinion, what we're trying to do is solve, for example, quantum optimization problems that can't be solved in years running on classical supercompute hardware. That's the ideal quantum supremacy advantage that everyone's looking for. So if you compare, if you compare supercomputers running for years, how much energy that is, to something that can be solved on, one dilution refrigerator kind of cooled down, right, in some seconds or some minutes, or, when things are fault tolerant, and we can do something like Shor's algorithm, right, for factoring. So I think they do use a lot of energy, definitely not as much as a supercomputer, training any of the GPT models or running indefinitely trying to solve an optimization problem.
Right. Yeah, that's a very interesting comment. And I think this also motivates all the researching community to move towards quantum computing instead of HPCs and supercomputing clusters. But yeah, that's a thought for some other day. One last question before we move forward with the webinar. And this question is from Dan. The question is that the k-partite graphs have a very interesting topology and properties associated with it that may be exploited for high-dimensional data analysis. So are there any data sets with all-to-all connectivity between clusters, but zero connectivity within each cluster?
The graphs we built from the graph I showed there are all-to-all connected. So so the underlying algorithm we're running is a max-cut algorithm, a sequentially applied max-cut algorithm. This is a hybrid quantum algorithm that was actually developed by the German Center for Artificial Intelligence. So we leverage this to apply it to a real world problem. And the full graph is maximally connected. And basically you prune it and you sequentially apply it. So the result at the end is not maximally connected. It's sometimes a bit sparse, yeah, but it ranges. So I encourage you to check out the paper. So I've posted a link to the preprint in the chat here if you'd like to know more technical details of the work.
Wonderful. Great. Yeah, perfect. And we will also share this link to the paper via email to all the participants. So yeah. Okay, yeah, time to move forward with the webinar. I think this is a good point to call in Celine from E.ON to talk more about what it is to work at E.ON.
Thank you. And hi, everyone. After a lot of, I would say, technical parts about what the guys are doing at E.ON, to focus on energy and making a huge change, I think we can have a little advertising block on the career at E.ON and what it is like to work at E.ON. So Jan, if you would like to go to the next slide. I brought some slides for you guys, but you can just skip through them, Jan, if you would like to, because it's all things that you find on our homepage, that you find on probably a lot of companies' homepages. So I thought what is most important is telling you about what I notice while working at E.ON, which is definitely our values. For example, that we put the customer first. Me as a recruiter, I obviously put the candidate first, the hiring manager first. We want to share a very good service. And I think that's what everyone would like to do. And that's one of our core values. So if you are someone who would like to make a change and do something good for someone else, that's definitely one of the things that we share. Also, I mean, all of the things that you see on the slide, technology, delivering what is seemingly impossible. I guess that is something that I noticed a lot when I recruit for new roles that I have not heard about yet. I'm always quite surprised about what everyone is working at or working on. I've worked for finance now, for the group innovation, for HR. It's a lot of different fields, and I think everything has, or all of the fields have some part of something impossible to them, which we want to solve, and everyone knows why they are here and what they are contributing. If you want to go to the next slide. Thank you. Just some benefits that you also find on our homepage. But as said in the introduction, I think what is most important is giving you an insight of, for example, why I work at E.ON, which can be insurance, can be employee pensions, but is mainly I was working for Innogy, which partly split into E.ON. And I wanted that culture back. And I found that, and I think that's one of the most important things for me as a human being, to be surrounded by people that cherish my work and that appreciate what I do every day, and that see the work and the competence I bring to the field and how I can support them. So this is definitely something that you would find here. It's a lot of different people, I would say. So the part of diversity is not just, oh, this is something that we put on our homepage and this is where we want to go, but we want to make everyone grow. So that means hiring people different ages, from different places, different knowledge, so that eventually we become a very big and strong force, I would say. And then how you can apply is definitely on our homepage. What you can apply for are the jobs that are advertised. If you think that there is something where you are slightly differ from, or your profile is a bit different than what the profile is we're looking for, then you can definitely still send your CV and we will have a look at it and may see, okay, well, this looks interesting. You can put your motivation there. Doesn't need a motivation letter though. And then we have a look at it. We do have a trainee program that you can also apply for, where you look into different stations of E.ON, different departments, and you can create and shape your career. So this is something that we would definitely like to support everyone in. And I guess that's the part for the career advertisement. If you have questions, let me know, please.
Wonderful. Thanks a lot, Celine. I think this was very interesting, at least for all the participants who are at a stage where they want to pivot to a quantum career, or they just are curious about how it is to work at E.ON. So thanks a lot, Celine, for highlighting that. Please keep the questions coming on the Zoom chat. We will quickly take them in a couple of minutes. But before that, I would like to share some more details about how you can already start working as a part of the Womanium Fellowship and the Quantum Solutions Launchpad on the E.ON project, which Corey and Jan just highlighted. So yeah, just recapping, the Quantum Solutions Launchpad provides an opportunity to all the student community, PhDs, postdocs, even industry professionals who want to now pivot into a quantum domain to start working with some excellent partners. E.ON is our latest partner over here, and we are hosting a very exciting project for all of you interested. For all those who are interested, you can take a minute and scan this QR code. This would directly point you to the website also linked below. So womanium.org/quantum/QSL enrolls. You can go to this particular webpage, fill in your details, submit your resume, and then our team will reach out to you to select the best fellows. This is a very, very exciting opportunity. You get to work with some of the amazing research scientists, including Corey, Dr. Corey at E.ON, and together we'll try to build some very interesting solutions. So yeah, I'll pause for a minute over here. I'll let the participants take a screenshot or just quickly scan the QR code. If someone does miss this slide, we will also reach out to potential fellows via mail after the webinar with the webinar recording as well. So you can, yeah, see that over there too.
One question from my side, Vardaan, how many fellows are we looking for and for what timeline?
Yeah, so the fellowship will start in the next couple of months, and the total duration of the timeline, we are looking for at least a 1-year kind of a project. This would be a part-time opportunity, of course, but in terms of fellows, we are looking for at least 3 to 4 fellows, some really talented PhDs, postdocs to work on this kind of an exciting problem right now. If there are any more questions, yeah, please put it on the chat, but after the webinar, please feel free to shoot those questions to me via email as well. I will be reaching out to all the participants with the webinar recording link and all the papers which have been shared in the chat. So yeah, we will try to compile all the questions, share them with E.ON. And yeah, Corey, Jan, Munib, thanks a lot for making this possible. We are very excited to start this journey together with E.ON, and I really look forward to receiving all the exciting applications for the fellowship positions from the participants we have here right now. Thank you, everyone.